I'm glad to introduce the last speaker, Dr. Hamish Deery. Hamish is a PhD student in the School of Psychological Sciences at the Monash University. Today, his talk will be aging is associated with a high glucose cost in hub regions of the metabolic network. Let's welcome him.
Thanks, Zen, and good morning, everybody. Some of you may have seen a session that I shared on Wednesday, the local organising committee symposium. Today's session is a supplement to that. I won't cover the entire brain-wide analysis that we undertook on the metabolic connectome, but today focus on particular hub regions. I have no disclosures. As the previous speakers have already shared, the human brain has a high energetic requirement, and its main fuel source is glucose. At the same time, the brain has a limited capacity to store glucose in the form of glycogen, which is the primary storage form in the periphery, in muscle and liver. Because of these characteristics, the human connectome must trade off minimising energy use with maximising communication efficiency. And we know the way that it does this is through organisation of the functional connectome. You see this in the bottom left-hand figure. So here we see a clustering of local modules indicated by nodes in the white and their edges by the black lines. So the energy constraints means that the organisation of the connectome has this local clustering of modules with highly efficient connections, meaning that connections between the nodes have to cross a relatively few paths. We also know that the human connectome is not adequately described purely by this local organisation. Hubs and their long-range connections, which you see in the red, are particularly important for global integration or information transfer across the brain. These play a similar role to major airports around the world. So if you think about airports like LAX or London, they're a central point for information coming in or flights coming in and going out. And disruption to these hubs will cause major problems in terms of information transfer, or in the example of airlines, we would have problems with global travel. And so we're interested to understand whether similar changes or dysfunction occurs in ageing in these hub regions. While hubs are particularly important for information transfer, they do come at what is often referred to as having a high wiring cost. This is indicated in the right-hand chart, where you can see that hub regions relative to non-hub regions have about a 4% higher cost of synaptic transmission. Before I share our current results, I'd just like to frame up some of the past research in this space, just to give you a bit more detail about what we're expecting to see in the metabolic hubs. We recently undertook a systematic review of 145 fMRI studies looking at functional changes in ageing. We found there is a reorganisation of the connectome, but particularly important to today's talk is that we see reduced connectivity of hub regions, particularly hubs in the frontal, parietal and occipital lobes. We also undertook a systematic review and meta-analysis, an ALE meta-analysis of how glucose changes in ageing in the brain. And we found 9 major areas or clusters of glucose hypometabolism. The largest clusters are in the frontal and temporal regions of the brain. So while this research is highly informative, as our previous speakers had shared, there are some limitations, particularly in the static analysis of glucose metabolism. It doesn't really allow us to understand the dynamic nature of glucose and how it evolves over time. So functional PET, developed by our group and others, as has been shared already, about 10 years ago, has been used to understand particularly changes in task-relevant regions while people perform tasks such as watching a checkerboard or finger tapping. With this work, the frame duration or frame rate has been pushed from minutes, now we're down to less than 10 seconds in some instances. So this allows us to establish a time series within individual subjects and to undertake connectivity and graphmetric analysis. The figures at the bottom are from some of our work where we found that metabolic connectivity is complementary relative to functional connectivity in the topology of the organisation of the connectome, but also in the relationships to cognition. So with that background, where our goal here was to investigate changes in the metabolic connectome in ageing and its relationship to cognition. And the primary focus of what I'll share today is we're interested in understanding how measures of the metabolic costs of the hubs, which we index via the metabolic rates of glucose changing in ageing, and its relative influence on the role of these hubs in information transfer. We had 4 hypotheses. The first is that there will be age differences in the metabolic connectivity, and that will be predominantly frontal and temporal, as we've seen in the static PET imaging. Secondly, that the metabolic hubs of older adults will show lower efficiency, so signals will need to cross more paths between the hubs and other regions of the brain. Thirdly, the glucose metabolism will be higher in the hubs than the non-hub regions because they have this higher wiring cost premium. And also there'll be a greater proportion of brain glucose used by older adults to support these hubs. And then finally, we looked at whether the efficiency of the metabolic hubs will be associated with better cognitive performance. And our expectation or hypothesis is that higher efficiency will lead to better cognitive outcomes. Again, for those of you who joined the session on Wednesday, you'll be familiar now with the METCON study. This is comprised of 40 younger and 46 older adults that we recruited from the local community. The mean age of the older group is 76 years and the younger group is 28 years, and approximately 50% male-females in each group. We consider this very much a normative ageing sample because the other demographic characteristics of the sample, measures like BMI, blood glucose levels, blood pressure, are all within normative ranges within the adult Australian population. Participants first underwent a cognitive test battery, indexing memory, executive function and processing speed. They then underwent a simultaneous fMRI FPET 90-minute simultaneous scan while they were watching a movie of a drone flying over the Hawaii Islands. As others have touched on with functional PET, we use a bolus plus a constant infusion method. We found this optimises signal-to-noise ratio across the scan. We reconstructed the PET images and binned them into 16-second intervals. And I just wanted to mention that we have looked at both anatomical and functional parcellations. The work I shared on Wednesday was based on the functional parcellation. Here I'm going to focus more on the anatomical parcellations, but the full work is available in a paper that I'll share the link to at the end. So I wanted just to share the results at the whole brain level before we look at the metabolic hubs. You recall that we hypothesise or expect that there'll be stronger connectivity in the frontal and temporal regions of the brain, and that will decline in ageing. And that's really what we're seeing in this between-region connectivity matrices. If you look on the right-hand side, the red squares indicate where the connectivity is higher in younger than older adults, and that is the case for both the frontal and temporal regions within, and then also across or between the regions. So if we overlay the yellow shading, you can see particularly between the left and right frontal areas and the temporal regions, but also medially and to the parietal regions. So this very much supported our hypothesis that would be reduced connectivity in the older brain. Just to spend a minute on how we defined the hub regions. There is no single agreed definition in the literature around how to define a hub region, although it's quite common to use graph metrics like between the centrality degree and global efficiency. So we adopted an approach of identifying hubs as regions that are above 1 standard deviation on at least 2 of these measures. In doing so, we identified 13 hub regions in the frontal areas of the brain, the motor regions, precentral, postcentral gyri, occipital regions, and the cingulate gyrus and the precuneus. These map quite well to known hub regions identified through fMRI. So we started by looking at the differences between the age groups in the efficiency in these hub regions. The chart on the top right is measuring local efficiency. So again, this is the number of paths that the signal needs to cross between the hub and the other regions in the local network. And here the blue is indicating a reduction in ageing, so lower efficiency in older adults. And we see really across the hubs, across the entire cortex, that there's a reduction in local efficiency in older adults. For global efficiency at the bottom, younger adults had higher efficiency in the frontal poles and the middle and superior frontal gyri, indicating that signals from these frontal regions to the rest of the brain are needing to cross more paths in the older adults. So we conclude from this that hub local efficiency in younger adults help to minimise the cost of local network communication via fewer paths to connected nodes, and that for younger adults, the frontal hubs are central or important in the efficient and connected facilitation of communication across the brain. Next, we're interested to understand whether the metabolic hubs have a higher wiring cost, as has been established in the fMRI research. In the chart here, you're seeing the red line is the average CMR glucose, or metabolic rate of glucose, in the hubs relative to the non-hubs, and it was 4.1% higher. The individual bars are the participants, the 86 participants, and you can also see that the metabolic rates of glucose were higher in 83 of the 86 participants. So this very much supports our third hypothesis. We also looked at age differences in the rates of glucose metabolism in these hubs and found that on average there's a 16% lower rate in older relative to younger adults. So these results suggest that the metabolic hubs do have a higher glucose cost or wiring cost premium compared to non-hubs, and that older adults have a smaller glucose budget to support hub function. Next, we calculated what we referred to as the glucose cost index. This is simply the ratio of the metabolic rate of glucose to the hub graph metrics. This indicates the metabolic cost of the network communication as measured by the graph metrics. And in older adults, we see a higher glucose cost, reflecting hubs that have lower available glucose, as we'd seen on the previous slide, to support more paths between regions. In other words, they're less efficient. And we see this for both local efficiency and global efficiency. And again, the effect is particularly strong in the frontal regions of the brain. These results are suggesting that older adults use a larger proportion of their smaller glucose budget to support integration of hubs across the brain relative to younger adults, which they also do less efficiently. Finally, I just wanted to share the relationship between the hub function and cognition. And here we're using canonical correlation analysis, which identifies the multivariate pattern that maximises the correlation between the measures. And on the left-hand side, you can see that reduced global efficiency, particularly in the frontal, but also the motor regions, is associated with worse cognitive performance in episodic memory, visualospatial performance, and reaction time or processing speed across our cognitive battery. We found similar results for local efficiency, highly significant. These results are indicating that hubs are key players in network communication and that they're prone to age-related alterations that impair cognitive performance. So to sum up, we found that ageing is characterised by an altered metabolic connectome and reduced capacity of hubs to efficiently connect to other regions in the local network, and importantly, from frontal hubs to the rest of the brain. Metabolic hubs have a high value in information integration across the brain, but they also have a high wiring cost premium in terms of their high rates of glucose metabolism. Older adults have a higher glucose cost of cognition in that they have a smaller energy budget, and they use that less efficiently to integrate information across the cortex. And that pattern is associated with worse cognitive performance. So our results highlight the fundamental role that metabolism plays in supporting information transfer in the brain and the unique insights that metabolic connectivity provides into the ageing brain. Just finally, I'd like to acknowledge the wider Metcon team and particularly my supervisors. They really laid the groundwork for establishing the FPEP methods that we've used here. And as I mentioned, we published this work. There's a QR code to the paper in communications biology for those that are interested. So with that, thank you.